Okay, let's take a look at the next problem we have here. This problem is asking us to determine I of C whenever the time is at 1.2 seconds. So I of C 1.2 seconds. Where's our I of C? We see it's down here. Okay, so we're wanting to find this current that goes through there. And it's not very well drawn, but plus and minus. Okay, so taking a look at this, we see that we have a switch operator here, and initially this is closed to the top one. Then we come in here with, oh, a little crazy there. We come in here and we throw the switch to the other side, and that's going to cause switch to be closed over here. So this is our time before zero circuit. And then if we wanted to draw the other circuit, so this is the time greater than or equal to zero. Plus minus. Minus R2. Battery's a little high. Minus R1. And there we go. So the R2. Okay. So here, this is really what it would look like. Okay. Terminals, bam, and then bam. So we have two circuits, before time is equal to 0 and after time is equal to 0. Let's look at what's happening with these. So of course, we just have to assume we're going to operate at steady states where time is less than 0. So where we were saying we just come to it. So our battery from this battery current is going to leave there, come that way, down here. It'll follow this switch, this one that way, continue this way, go. And then it won't go down this branch because it's got an open terminal on it, so it'll bypass that. And then it'll go up that way. So effectively, it just skips this middle branch. So this middle branch isn't actually doing anything for us in the circuit. So let's just go ahead and do this for fun. So now let's take a look at the bottom one. Well, the bottom one, we see now that we have a battery that will supply current this way. It'll travel through the switch, go through the capacitor, loop back this way. It's going to see that this is open, so it won't go down there. And then it'll just come up through the battery again, creating its loop. So once again, we can just come in here, and since that branch isn't doing anything for us, we can just go ahead and get rid of it. Say goodbye, see you later. All right, so now we have two simplified circuits. And if we want to find the current through a battery at a certain point in time, then what we need to do is we need to write I of C time is equal to dVc certain time. That's what we wrote the voltage there. But do we know the voltage? Not quite yet. But how do we find the voltage? Well, if we go do the charging discharging equation from our equation sheet, so V of C at time t is going to be equal to V of C infinity plus V of C at time 0 minus V of C at infinity. So we get e to the minus t over tau. So if we can determine the voltages at these 2 points, then we can figure out what's going to happen in here. So we need to pick. We basically need to go through and determine this value, and then that value up there. So let's go through and see what we want to find out first. So let's go find V initial first. So V initial, if we look at the first circuit, we'll notice that from our assumption that this was operating in steady state for a long time. And what do we know from that assumption? From that assumption that we have plus minus, current runs through for a really long time, so it's going to clip itself out. So if this clips itself out, we just have those 2 open terminals. So really, there's no current running through here at all. No current, because we have an open terminal. So what does that mean for us? Well, we know that it's going to have, the wire will still have voltage in it, regardless of whether or not it actually has current flowing through it. So like we were saying before, since there's no current running through it, let's assume we start down here with 0 volts, 0 volts, come up through here to this battery, we'll pick up 6 volts, we'll have 6 volts up here, because we're passing through here, but we're not passing through with current, we're just going along the wire. There, this also has 6 volts. There, this will have 6 volts, and then right there as well, we'll also have 6 volts. Where we said there, we'll have 0 volts. So the voltage across these 2 points here for V of C is going to be equal to V of 1, the battery. Another way you can do that, just to prove this, is if you came over here and did a KVL, and we just walked around this loop. What we can say is that we're going to hit the minus terminal of V1 plus the voltage of R1 plus the voltage of R2 plus V of C is equal to 0. Well, if we know no voltage is going to be absorbed by the battery, by the resistors, then we can just say that therefore V of C is equal to V of 1, which is what we have here. So this V of C initial will equal 6 volts. Okay, so we got that. Now we need to look at V infinity. Let's take a look at V infinity. Let's go down to our much smaller circuit down here. And I forgot to write this, but this is V of 2. And what voltage was that? 3 volts. Okay. Yeah. So now let's take a look here. So if we wanted to let this run for infinity, like we said before up here, if we let it run to forever, that capacitor is going to clip itself out again. So I'll just go ahead and like that. And now we can do the same thing as before. So we can do the KVL on it. Let's just, that loop, minus V2 plus VR2 plus VR3 plus V of C is equal to 0. We know that these are going to go to 0. They're not absorbing anything. So therefore, V of 3 is equal to V of 2. So V of C at infinity is going to be equal to 3 volts. Go. Okay. So the last thing we're going to need is the equivalent value to find the time constant. Okay. So how do we find the time constant? Here, let's go ahead and do this. So we say that time constant for capacitor is equal to RC. Well, we have our capacitance value. Where do we get our resistance value from? Well, since we're analyzing the time goes to infinity circuit, what we need to do is pull out our favorite method, Thevenin. The reason why you were learning it a lot is to also apply it to different methods like we're about to see here. So if you took this circuit, notice there's actually a VOC there. So if you took that circuit and then you applied all the steps, so all right, apply Thevenin steps, where you took the battery and changed it into just a wire, and then you find RThev, what you would do is you would end up with a circuit like this. You would get R2 there, R3 here. You would find that these two are in series. And just to save a little bit of time, we're going to do this. C is equal to VC. R series is just going to be R2 plus R3. Will be R2. We said was 3 kilo ohms. Then R3 is 1 kilo ohms. So this will be 4 kilo ohms. So then now we see that is R Thevenin, which is equal to equivalent resistance. So that's what we're going to use for right there. Okay. So almost there. So tau C is equal to 4 kilo ohms times capacitance value was 100 microfarads. So therefore our time constant is going to be equal to, and real quick, that's our equivalent. .4. Okay. So now that we have that, we can come in here and we can start filling stuff out. So V of C at 1.2 seconds is equal to infinity value we said was 3 plus the initial value 6 minus 3 to the minus. We said this is 1.2. This is 0.4 for tau. So therefore, V of C at 1.2 is going to be equal to Better idea. So yes, we need to find the time at 1.2, but notice here that this needs to be as a function of time rather than just time, because we can't take a derivative of a constant number that will give us 0. So we need to leave time in there. So then now this will just simplify down to 3 plus 3e negative 0.4, actually 0.4 inverse is equal to about 2.5. So this will be minus 2.5t. And then now what we can do is to find the current I of C at t will be equal to dvc with respect to time. So this will be t 3 plus 3e to the minus 2.5t. When we do that, we'll get negative 3 times 2.5. See here, 2.5 times capacitance value C. Then we're going to keep e to the minus 2.5 t. And when we simplify this down, this will give us negative 7.5 c e to the minus 2.5 t. And then finally, we just got to plug in I of C at 1.2 will be equal to 7.5. C we said was 100 microfarads. And then this is e to the minus 2.5 2. I of C of 1.2 is equal to and we get a value of negative 0.037 amps. Okay. Now you might be wondering, why is that? Why is it a negative current? Well, let's take a look. If we go and find the actual voltage value, like we were doing before, so this would be second e to the minus 2.5 this capacitor voltage at 1.2 is 3.149 volts. And you'll notice this battery here is only 3 volts. So our voltage of C at 1.2 is greater than the voltage of 2. So it's actually going to be pushing the current the opposite direction because it has more voltage. So current moves from higher voltage to lower voltage. That's why the current direction is negative. So it's opposite of what we assumed. All right, so I filled out the page. I'll see you in the next problem.